Chapter 3. Valve and Actuator Types.
Next, we turn to valve body types. I'd like to introduce the basic role and requirements of the control valve body. A control valve is a device that regulates the flow rate of a fluid by changing the position of the valve plug or disc using force transmitted from the actuator. To perform this function properly, four conditions must be met simultaneously. First, it must contain the fluid without external leakage. Second, it must have adequate capacity for the intended service. Third, it must withstand the erosion, corrosion, and temperature influences of the process fluid. And fourth, it must have appropriate end connections to mate with adjacent pipelines, along with attachment means to transmit actuator thrust to the plug stem or rotary shaft. Various styles of valve bodies have been developed over time. Some are widely used, while others are used less frequently for specific service conditions. In the following section, we will cover the representative styles commonly used today.
Among globe valves, I'd like to introduce the single-port valve body, which is the most common. The single port is the most frequently used body style and is characterized by its simple construction. It is available in various forms such as globe, angle, bar stock, forged, and split constructions. Single-port valves are generally specified for applications with stringent shutoff requirements. For this purpose, they use metal-to-metal seating surfaces or adopt a soft seating method that forms a seal using PTFE or other composition materials.
I'll now discuss the unbalanced force issue, sizing, and cage construction of single-port valves. In single-port valves, since high-pressure fluid normally loads the entire area of the port, an unbalanced force is created, and this force must be considered when selecting the actuator. While single-port valves are most popular in smaller sizes, they can often be used in 4-inch to 8-inch sizes if high-thrust actuators are used. Many modern single-seated valve bodies adopt a cage or retainer-style construction, which secures the seat ring cage, guides the valve plug, and provides a means for establishing particular flow characteristics. Additionally, retainer-style trim is easy to maintain, offering the advantage of changing flow characteristics simply by replacing the plug. Figure 3.1 shows representative styles of these single-ported globe-style valve bodies.
This shows the basic structure of a globe-style valve body with a single-port configuration. I'd like to introduce cage-style single-seated valve bodies and angle valves. Single-seated valve bodies with cage or retainer construction can be easily modified by changing trim parts to provide reduced capacity flow, noise attenuation, or the reduction or elimination of cavitation. The two styles shown in Figure 3.1 are widely used in process control applications, particularly in sizes from 1 inch through 4 inch. The normal flow direction most often goes up through the seat ring. Meanwhile, angle valves are almost always single-ported, as shown in Figure 3.2. These valves are commonly used in boiler feedwater and heater drain service, as well as in piping schemes where space is at a premium and the valve must also serve as an elbow. The angle valve shown here adopts a cage-style construction.
This is the appearance of an angle-style control valve body with flanged connections. I'll now introduce bar stock valve bodies and high-pressure single-ported globe valves. Some bodies may feature screwed-in seat rings, expanded outlet connections, restricted trim, and outlet liners to reduce erosion damage. Bar stock valve bodies, shown in Figure 3.3, are primarily specified for corrosion service applications in the chemical industry. These bodies can be machined from any metallic bar stock material, or from some plastics. When exotic metal alloys are required for corrosion resistance, a bar stock valve body is normally less expensive than one produced from a casting. High-pressure single-ported globe valves, shown in Figure 3.4, are commonly used in gas and oil production. Available variations include cage-guided trim, bolted body-to-bonnet connections, and self-draining angle versions.
These are valve bodies precision machined using bar stock material.
This is a globe-style control valve body designed to withstand high-pressure environments.
I'd like to introduce the ratings of high-pressure globe valves and the balanced plug cage-style valve bodies. The flanged versions shown in Figure 3.3 and Figure 3.4 are available with ratings up to Class 2500. Moving on to the balanced plug cage-style valve body. This is single-ported in the sense that it uses only one seat ring, as shown in Figure 3.5. The advantage of this style is that it provides the benefits of a balanced valve plug, which were originally associated only with double-ported valve bodies within a single-port structure. The cage trim is responsible for valve plug guiding, seat ring retention, and flow characterization simultaneously. In addition, a sliding piston ring type seal is placed between the upper portion of the plug and the cage cylinder wall, which virtually eliminates leakage of the upstream high-pressure fluid into the lower-pressure downstream system. This is a valve body featuring cage-style trim, a balanced valve plug, and a soft seat.
I'll now explain the operating principle of the cage-guided balanced plug valve body. The core of this structure is that downstream pressure acts on both the top and bottom sides of the valve plug simultaneously. As a result, most of the static unbalance force acting on the plug is nullified. By reducing the unbalance force, the valve can be operated with smaller actuators than those required for conventional single-ported valve bodies. The trim is designed to be interchangeable, allowing for the selection of several flow characteristics or the installation of noise attenuation or anti-cavitation components. In most trim designs, the standard direction of flow is in through the cage openings and down through the seat ring. Various material combinations are available, with sizes up to 20 inches and pressure ratings up to class 2500. Meanwhile, the high-capacity version, which is an adaptation of this cage-guided body, was specifically designed for noise applications, such as high-pressure gas-reducing stations where sonic gas velocities often occur at the valve body outlet.
Let's look at the high-capacity, cage-guided valve body. This design targets environments where gas velocities reaching sonic speeds frequently occur at the outlet of conventional valve bodies. As you can see in Figure 3.6, it features oversized end connections with a streamlined flow path while maintaining the easy trim maintenance inherent to cage-style constructions. Using noise abatement trim can reduce overall noise levels by as much as 35 decibels. Cageless versions with bolted seat rings are also available, with end connection sizes up to 20 inches, class 600, and versions for liquid service. The flow direction depends on the intended service and trim selection, with unbalanced constructions normally flowing up and balanced constructions normally flowing down. Next, port-guided single-port valve bodies are typically limited to a maximum pressure drop of 150 psi, or 10 bar, and are characterized by their susceptibility to velocity-induced vibration. This is a high-capacity valve body featuring cage-style noise abatement trim.
Starting with the limitations of port-guided single-port valve bodies, this type typically uses screwed-in seat rings, which can be difficult to remove after use. Next, I'll introduce the characteristics of double-ported valve bodies. In a double-port design, the fluid acts to open one port while simultaneously closing the other, so the dynamic force acting on the plug tends to be balanced. Because these dynamic forces are reduced, a smaller actuator can be selected compared to a single-ported valve body with similar capacity. However, double-ported valve bodies are usually supplied only in larger sizes, 4 inches or larger, and have a higher flow capacity than single-ported valves of the same line size. Additionally, many double-ported bodies are reversible, so the valve plug can be installed as either push-down to open or push-down to close, as shown in Figure 3.7.
This is a reverse-acting double-ported globe-style valve body. I'll now discuss the leakage class and plug guiding methods for double-ported valves. Metal-to-metal seating generally provides Class 2 shutoff capability, although Class 3 capability is also possible. The application varies depending on how the plug is guided. Port-guided plugs are frequently used for on-off or low-pressure throttling service. In contrast, top and bottom guided plugs ensure stable operation, even under severe service conditions. Therefore, the choice of shutoff performance and guiding method must be carefully decided based on the actual operating conditions.
The control valve body shown in Figure 3.7 is assembled for push-down to open action, where the plug is pushed down to open the valve. In this case, the valve plug is essentially balanced, so only a relatively small amount of actuator force is required to operate the valve. Double-ported designs are typically used in refineries for highly viscous fluids, or where there is a concern about dirt, contaminants, or processed deposits on the trim. Next, I would like to introduce three-way valve bodies. Three-way valves perform flow mixing services by converging fluids or flow splitting services by diverging them through 3 pipeline connections. The best designs use cage-style trim to ensure positive plug guiding and ease of maintenance. Variations include trim materials selected for high-temperature service, and end connections can be specified using standard methods, such as flanged, screwed, or but weld to mate with almost any piping scheme. I will now discuss actuator selection for three-way valves and butterfly valve bodies. For three-way valves, actuator selection must be carefully considered, especially for constructions with an unbalanced plug. Figure 3.8 shows a balanced plug style, three-way valve body with a cylindrical plug in the down position. In this position, the bottom common port is open to the right-hand port, and the left-hand port is shut off. This construction can be used for throttling control at the mid-travel position for either converging or diverging fluids. Next is the butterfly valve body, a type of rotary valve. As seen in Figure 3.9, it requires very little space for installation and provides high capacity with low pressure loss through the valve. It is particularly economical for larger sizes and in terms of flow capacity per investment dollar.
This is the structure of a three-way valve equipped with a balanced valve plug.
This is a high-performance butterfly-type control valve capable of precise control.
I would like to introduce the control characteristics and piping mating conditions of butterfly valves. These are divided into two types based on the disc rotation method. Conventional contoured discs provide throttling control within a rotation range of up to 60 degrees. On the other hand, patented dynamically streamlined discs are designed for applications requiring 90-degree rotation. The valve body mates with standard raised face pipeline flanges. However, it should be noted that if the valve is large or the differential pressure is high, the operating torque can increase significantly, which may require high output or large actuators. Continuing with the application range and actuator selection criteria for butterfly valves. These valves are also supplied for nuclear power plant applications with very stringent leakage requirements. For the liner, nitrile or PTFE can be used to achieve good shutoff and corrosion protection. Standard sizes are available up to 72 inches for various control valve applications. The actuator varies by size. For small diameters, traditional diaphragm or piston pneumatic actuators, as well as modern rotary styles, can be used. For large diameters, high-output electric or long-stroke pneumatic cylinder actuators may be required. The flow characteristic is approximately an equal percentage characteristic, and they are applied to both throttling and on-off control.
This is a rotary shaft type control valve featuring a V-notch ball. I would like to introduce the structure and flow characteristics of V-notch ball control valves. First, soft seat construction can be achieved by using a liner or by including an adjustable soft ring in the body or on the face of the disc. This valve is similar to a conventional ball valve, but it is characterized by a patented contoured V-notch machined into the ball, which creates an equal percentage flow characteristic. Thanks to this, rangeability, control, and shutoff capability are all excellent. They are used in the paper industry, chemical plants, sewage treatment plants, power industry, and petroleum refineries. The straight-through flow design results in low-pressure drop, and it is suitable for controlling erosive or viscous fluids, paper stock, or slurries containing entrained solids or fibers. They use standard diaphragm or piston rotary actuators.
I'd like to introduce the sealing behavior of V-notch ball valves and the subsequent eccentric disc valves. The V-notch ball remains in contact with the seal during rotation, which produces a shearing effect as the ball closes and minimizes clogging. Seal rings are available in heavy-duty or PTFE-filled compositions to ensure rangeability in excess of 300:1. End connections are available as flangeless or flanged, and they mate with class 150, 300, 600, or DIN flanges. Next, eccentric disc control valves provide effective throttling control and exhibit a linear flow characteristic through a 90-degree rotation range. Because the disc is eccentrically mounted, it pulls away from the seal as it begins to open, minimizing seal wear. These are available in sizes up to 24 inches and are compatible with standard ASME flanges.
This is a rotary shaft control valve with an eccentric disc structure.
Let's summarize the applications and control limits of eccentric disc rotary shaft control valves. They use standard pneumatic diaphragm or piston rotary actuators. The standard flow direction depends on the seal design. Reverse flow results in reduced capacity. These valves are intended for general service applications that do not require precision throttling control. Due to their lower cost relative to other control valve styles, They are frequently applied in large-size and high-temperature applications. However, the control range is only about one-third as large as that of ball or globe-style valves. Consequently, additional care is required in sizing and application to eliminate control problems associated with process load changes. They work quite well for constant process load applications. I'd like to introduce the erosion resistance and seat life of eccentric plug control valves. These valves combat erosion with a rugged valve body and trim design, handling temperatures up to 800 degrees Fahrenheit, 427 degrees Celsius, and shutoff differential pressures up to 1,500 psi, 103 bar. The path of the eccentric plug minimizes contact with the seat ring when opening, which reduces seat wear and friction, prolonging seat life and improving throttling performance. Thanks to the self-centering seat ring and rugged plug, tight shutoff is possible in both forward and reverse flow. The plug, seat ring, and retainer can be selected in hardened materials, including ceramics, to increase erosion resistance. Additionally, for higher capacity requirements, designs offering a segmented V-notch ball in place of the plug are available.
Let's look at the eccentric plug rotary control valve. This valve is suitable for erosive, coking, and other hard-to-handle fluids, providing both throttling and on-off operation. Both flanged and flangeless versions feature streamlined flow passages and rugged metal trim components to ensure dependable service in slurry applications. In fact, they are widely used in the mining, petroleum refining, power, and pulp and paper industries. Next, we will cover the methods of installing control valves in pipelines. Generally, 3 methods are used: screwed pipe threads, bolted gasket flanges, and welded end connections. Among these, screwed end connections are common in small control valves and offer the advantage of being more economical than flanged connections.
Next, we turn to connections and bonnets.
I'll now introduce screwed end connections and bolted gasket flanges for control valves. In screwed connections, a tapered female NPT national pipe thread is typically machined into the valve body. This forms a metal-to-metal seal by wedging over the mating male threads on the pipeline ends. This style is usually limited to valves not larger than 2 inches and is not recommended for elevated temperature service. One inconvenience is that during maintenance, to remove the valve body from the pipeline, a flanged joint or union connection must first be broken to allow the valve body to be unscrewed. In contrast, flanged end valves are easily removed from the piping and are suitable for the full range of working pressures for which most control valves are manufactured. Figure 3:13 summarizes the popular varieties of bolted flange connections.
These are the various bolted flange connection types commonly used in industrial sites.
I'd like to introduce flanged end connections and their representative types. Flanged ends can be used in a temperature range from absolute 0 to approximately 1,500 degrees Fahrenheit, 815 degrees Celsius, and are applicable to all valve sizes. The most common types are flat face, raised face, and ring-type joint. The flat face variety is a structure where 2 matching flanges make full face contact with a gasket clamped between them, and it is commonly used in low-pressure cast iron and brass valves. This construction has the advantage of minimizing flange stresses caused by the initial bolting up force. The raised face flange features a circular raised face with an inside diameter the same as the valve opening, and an outside diameter slightly smaller than the bolt circle diameter. Concentric circular grooves are machined into the raised face to improve sealing and ensure resistance to gasket blowout. Now let's look at the application range of raised face flanges and the ring-type joint flange. Raised face flanges are used in a pressure range up to 600 sig, 41.4 bar, and temperatures up to 1,500 degrees Fahrenheit, 815 degrees Celsius by combining various gasket and flange materials. This style is normally standard on Class 250 cast iron bodies and all steel and alloy steel bodies. The ring-type joint flange looks similar to the raised face flange, but it differs in that a U-shaped groove is cut into the raised face concentric with the valve opening. The gasket consists of a metal ring with either an elliptical or octagonal cross-section. When the flange bolts are tightened, this gasket is wedged into the groove of the mating flange, creating a tight seal. The gasket material is typically soft iron or Monel, which is a trademark of Inco Alloys International, but it can be manufactured from almost any metal.
I'll now cover the high-pressure application of ring joint flanges and welding end connections. Ring joints form an excellent joint at high pressure and can be used up to 15,000 sig, 1,034 bar. However, they are generally not used at high temperatures and are provided only on steel and alloy valve bodies when specified. Next, let's look at welding end connections. Welding ends are leak-tight at all pressures and temperatures and are economical in terms of first cost. On the other hand, they are more difficult to remove from the pipeline and are obviously limited to weldable materials. As shown in Figure 3.14, there are two types of welding ends, socket welding and butt welding.
These are the common welded end connection methods, frequently used for valve connections. I'd like to introduce the two types of welding ends, socket welding ends and butt welding ends. Socket welding ends are prepared by boring a socket with an inside diameter slightly larger than the pipe outside diameter into each end of the valve. The pipe slips into this socket, butts against a shoulder, and is then joined to the valve with a fillet weld. A characteristic of socket welding ends is that for a given size, the dimensions are the same regardless of the pipe schedule, and they are usually furnished in sizes through 2 inches. Butt welding ends are prepared by beveling each end of the valve to match the bevel on the pipe, and the two ends are then butted and joined with a full penetration weld. This joint is applicable to all valve styles, and the end preparation must differ for each pipe schedule. For control valves, these are typically provided in sizes 2.5 inches and larger.
Now we will discuss the second method of welding ends, butt welding, and the function of the valve bonnet. Butt welding ends are prepared by beveling both ends of the valve to match the bevel of the pipe end, and the two ends are joined with a full penetration weld. This method is used for all types of valves, but it is characterized by the fact that the end preparation must vary according to the pipe schedule. In control valves, this is typically applied to larger sizes of 2.5 inches or more. However, when welding a valve body into the pipeline, care must be exercised to prevent excessive heat from being transmitted to the valve trim parts, and trims made of low-temperature composition materials must be removed before welding. Moving on, the bonnet is the part of the body assembly through which the valve plug stem or rotary shaft moves. As seen in Figure 3.15 in globe or angle bodies, the bonnet becomes the pressure-retaining component for one end of the valve body. Additionally, the bonnet provides a means of mounting the actuator to the body and houses the packing box. Rotary valves generally do not have bonnets.
This is a typical configuration of the valve bonnet, flange, and the stud bolts used to secure them. I'd like to introduce how packing is housed in rotary valves and the various methods for connecting the valve body and bonnet. In some rotary shaft valves, the packing is housed within an extension of the valve body itself, or the packing box is configured as a separate component bolted between the valve body and bonnet. In a typical globe-style control valve body, the bonnet is made of the same material as the valve body or an equivalent forged material. This is because the bonnet is also a pressure-containing member subject to the same temperature and corrosion effects as the body. There are several ways to connect the body and bonnet, and the most common is the bolted flange type. Figure 3.15 shows a type where the flange is integral to the bonnet, and Figure 3.3 shows a type where a separable, slip-on flange is held in place with a split ring.
I'll now discuss various variations of bonnet connections and how the bonnet handles sealing in cage trim bodies. In the high-pressure globe valve body shown in Figure 3.4, the bonnet is screwed into the valve body. Figure 3.9 is typical of rotary shaft control valves, where the packing is housed within the valve body and a bonnet is not used. Here, the actuator linkage housing is not a pressure-containing part, but simply a cover to enclose the linkage for safety and environmental protection. In bodies using cage or retainer-style trim, the bonnet provides the loading force to prevent leakage between the bonnet flange and valve body, as well as between the seat ring and the valve body. Tightening the body bonnet bolting compresses a flat sheet gasket to seal the body bonnet joint, compresses a spiral wound gasket on top of the cage, and compresses another flat sheet gasket below the seat ring to provide the seat ring body seal.
I'd like to explain the bonnet's function in aligning the cage and plug, and the two methods for retaining the packing. The bonnet aligns the cage, which in turn guides the valve plug, ensuring that the valve plug stem is properly aligned with the packing. As mentioned, the conventional bonnet on a globe-type control valve houses the packing. The packing is typically held in place by a packing follower,
which is secured by a flange on the yoke boss area of the bonnet. This is the method shown in Figure 3.15. An alternative is to secure the follower with a screwed gland, as seen in Figure 3.3. This method is compact and often used in small control valves, but it has the disadvantage that the user cannot always be certain of the thread engagement. Therefore, caution is required when adjusting packing compression while the valve is in service. Most bolted flange bonnets have an area on the side of the packing box that can be drilled and tapped.
I'll now cover the use of the bonnet side opening and extension bonnets. The drilled and tapped opening on the side of the bonnet is usually closed with a standard pipe plug, but it is opened for two specific cases. First, when it is necessary to purge process fluid from the valve body and bonnet, this opening is used as a purge connection. Second, it is used to detect leakage from the first set of packing or from a failed bellows seal. Next, extension bonnets are used in high or low temperature service to protect the valve stem packing from extreme process temperatures. Standard PTFE valve stem packing is effective for most applications up to 450 degrees Fahrenheit, 232 degrees Celsius. However, it is susceptible to damage in low-temperature processes if frost forms on the valve stem. This is because frost crystals can cut grooves into the PTFE, creating leakage paths for process fluid along the stem.
This is an extension bonnet designed to raise the position of the actuator.
I'd like to discuss the structural differences and material selection criteria for extension bonnets. Extension bonnets move the packing box of the bonnet far enough away from extreme process temperatures so that the packing temperature remains within the recommended range. Extension bonnets are divided into cast and fabricated types. The cast extension in Figure 3.16 is advantageous for high-temperature service because its higher heat emissivity provides a better cooling effect. Conversely, smooth surfaces, such as the fabricated type made from stainless steel pipe in Figure 3.17, are preferred for low-temperature service, as the primary concern there is preventing heat from entering. In either case, the wall thickness of the extension should be minimized to reduce heat transfer. Additionally, stainless steel is generally preferred over carbon steel due to its lower thermal conductivity coefficient. This is a view of a valve body equipped with a separately fabricated extension bonnet.
I would like to introduce the material selection for extension bonnets and bellows seal bonnets. The key for extension bonnets is to minimize the wall thickness to reduce heat transfer along the bonnet. For the same reason, stainless steel is preferred over carbon steel due to its lower coefficient of thermal conductivity. In cold service, heat influx from the outside is the primary concern, so insulation can be added around the extension to further block heat influx. Next is the bellows seal bonnet. This is used when leakage along the stem must be suppressed to less than 1 × 10 to the power of -6 cc/SEC based on helium, essentially when zero leakage is required. This structure, shown in Figure 3.18, is adopted when handling toxic, volatile, radioactive, or very expensive process fluids, and it protects the stem and valve packing from contact with the process fluid.
This is the structure of a bellows seal bonnet with EnviroSeal technology applied.
I will now introduce the safety design, temperature limits, and 2 manufacturing methods for bellows seal bonnets. Placing a standard or environmental packing box structure above the bellows acts as a double safety device, preventing catastrophic leakage even if the bellows ruptures or fails. As with other control valve pressure and temperature limits, this pressure rating also decreases as the temperature rises. Therefore, when choosing a design, one must consider whether proper inspection and maintenance are possible after installation, and the bellows material must be carefully selected to ensure maximum cycle life. There are 2 types of bellows seals: the mechanically formed type in Figure 3.19 and the welded leaf type in Figure 3.20. The welded leaf type has the advantage of a lower total package height.
This is the detailed structure of a mechanically formed bellows.
I would like to discuss the service life characteristics of welded leaf bellows. As seen previously, the welded leaf type has the advantage of a lower package height, but its service life may be limited due to the manufacturing method and inherent design characteristics. In other words, it must be considered that reducing height may be disadvantageous in terms of cycle life. This drawing is identified by code 12A7837A. Next, we turn to packing systems.
I will introduce the standard PTFE veering packing drawing. This drawing shows the structure of standard PTFE veering packing used to seal the control valve stem. It is a representative packing configuration that ensures sealing while keeping friction low by stacking multiple rings with V-shaped cross-sections around the stem. The corresponding drawings are identified by codes 13A9775, ENB 2565/IL.
I will now introduce the welded leaf bellows drawing and an overview of control valve packing. The welded leaf bellows in Figure 3.20 has a limited service life, as mentioned, whereas the mechanically formed type is taller but offers better repeatability in the manufacturing process. Now, moving on to control valve packing. Most control valves use a packing box, where the packing is secured and adjusted using a flange and stud bolts, as shown in Figure 3.23. Packing materials are selected based on expected service conditions and whether the application requires compliance with environmental regulations. If sacrificial zinc washers are used, their installation position is specified in the drawing. This shows the application of single PTFE veering packing.
Now, I would like to introduce the packing materials used to seal the stem of a control valve. Figure 3.21 provides a comprehensive overview of typical packing material arrangements used for globe-style valve bodies. First, the PTFE veering is a plastic material with an inherent ability to minimize friction. Since V-shaped rings are spring-loaded and self-adjusting within the packing box, separate packing lubrication is not required. It is resistant to most known chemicals, except for molten alkali metals. However, for proper sealing, the stem surface must be extremely smooth, at a level of 2 to 4 microinches RMS, and leakage will occur if the stem or packing surface is damaged. The recommended operating temperature is from -40 to +450 degrees Fahrenheit, which is -40 to +232 degrees Celsius. One point of caution is that PTFE is not suitable for nuclear service because it is easily destroyed by radiation. For high-temperature nuclear environments or where low chloride content is required, laminated and filament graphite, specifically grade GTN, is appropriate.
This is a comprehensive arrangement of various packing materials applied to globe-style valve bodies. I'd like to continue introducing the characteristics of graphite packing. Graphite provides leak-free operation, high thermal conductivity, and a long service life, but in exchange, it produces high stem friction and resultant hysteresis. It is virtually unaffected by most hard-to-handle fluids and high radiation environments. The operating temperature range is very wide, from cryogenic temperatures up to 1,200 degrees Fahrenheit or 649 degrees Celsius. Lubrication is not required, but if the packing box temperature exceeds 800 degrees Fahrenheit or 427 degrees Celsius, an extension bonnet or steel yoke should be used. From here, we move on to U.S. regulations regarding fugitive emissions. Fugitive emissions refer to non-point source volatile organic emissions resulting from process equipment leaks. Equipment leaks in the United States are estimated at over 400 million pounds per year, and valves and pumps have been identified as key emission sources. Accordingly, the U.S. has established strict regulations requiring the implementation of leak detection and repair programs, abbreviated as LDAR.
I'll now explain how the LDR program specifically operates. In the context of valves, fugitive emissions refer to leakage to the atmosphere caused by packing seal or gasket failures. This program requires the monitoring of all valves, regardless of whether they are control valves or non-control valves. The monitoring interval is determined by the percentage of valves found to be leaking above a threshold level of 500 ppmv, though some cities use a stricter criterion of 100 ppmv. This level of leakage is so slight that it cannot be seen or heard, so sophisticated portable monitoring equipment is required for detection. Detection is performed using a sniffing method at the valve packing area, following the Environmental Protection Agency, or EPA, protocol. This is a costly and burdensome process for industry. However, the regulations allow the monitoring period to be extended up to 1 year if the facility can demonstrate that the percentage of leaking valves is consistently kept very low, specifically less than 0.5% of the total valve population.
Now, I'd like to introduce low-leakage packing designs that allow for the extension of the monitoring interval. Figure 3.22 schematically shows the opportunity to extend the measurement, or monitoring, interval.
Packing systems designed for extremely low leakage improve both seal life and performance, supporting the objective of annual monitoring. A representative example is the EnviroSeal packing system. The enhanced seals of this system incorporate 4 key design principles. First, pliable seal material is securely contained using an anti-extrusion component. Second, the valve stem or shaft is properly aligned within the bonnet bore. Third, constant packing stress is applied using Belleville springs. Fourth, the number of seal rings is minimized to reduce consolidation, friction, and thermal expansion. Meanwhile, in the traditional valve selection process, valve designs were chosen based on pressure and temperature capabilities, flow characteristics, and material compatibility.